Okay, great. So thanks for coming today, everyone. Per last week, everyone's going to be on mute by default. Feel free to ask any questions in the chat, send them to Jen. And if you want, please note the slide number that your question pertains to. And just as a quick intro, my name is Pat Callahan. I'm a clinical research coordinator with the Rankin Lab, coming up on about 2 years now at the Mac, and I've been doing a lot of coding with R in those last several years. So today we're going to take a little look at R kind of in the context of data science. So some of my assumptions for today are that you have maybe a little bit of familiarity with R at minimum, and this presentation won't necessarily be as practical as the Tidyverse one from last week, but I'm going to include a lot of technical details ranging from really basic beginner topics up to some more intermediate issues and troubleshooting steps that I think will be useful to people here today. So there's going to be a lot of content that I'm trying to cover, and I really don't expect everyone to completely understand everything this first time around. My recommendation is that you kind of take note of what you don't understand as we go through this, maybe ask some questions after the presentation, and maybe Google some of the topics as well. So with that, what will we cover today? Well, my goal is to first give you a little bit of an overview about R and kind of its place within the data science world. I want to give everyone a really simple quick start guide on using kind of basic tangible things that you'll need to do in R. And from there, I'll be covering a really wide variety of topics that will help you better use and understand the R language. So with that, let's go ahead and take a look at R within the world of data science. So I think the first thing to consider here is, what is data science? And when I think about it, I think of it as a bit of a massive amorphous field that can be very broadly thought of or cut into the cross sections of math and statistics, domain expertise, and coding. So math and statistics here I'm using a little bit loosely or a little bit in a more nebulous fashion, but it's relatable if you think about it in terms of things like frequentist or Bayesian statistics or model building. And I think there's a lot of great mentorship available at the Mac about what kind of stats you should be using and when it should be applied to different situations when you want to build models. And even more so, there's a lot of domain expertise. So a lot of you here today are neuropsychologists or otherwise deep within kind of neuroscience research. And so you have domain expertise within the field of neuroscience or neurodegeneration. And so there's a lot to draw on at the Mac when it comes to having domain expertise and knowledge about statistics. The coding aspect of data science, however, is where I think that there may be a little bit of lack of knowledge at the Mac, or kind of a lack of, I suppose, unity in how people are coding. And I think that if people were to improve their coding skills, we'd really see a lot more or a lot quicker breakthroughs in kind of what we do with our analyses here at the Mac. So my goal is to really help you improve your data science skills just from the coding perspective today. So in order to do that, I think it's useful to first look a little bit at R's history. And so R is an implementation of the S language, which was made by Ross Ihaka and Robert Gentleman at the University of Auckland in New Zealand back in 2000. And it reached this latest milestone, the 4th major release, back in April of this year. So given that it's 20 years old now, I suppose depending on context, you can say it's either a new language, it's an old language, or it's midlife. And at this point, I think I'd just say that R is a well-established and well-maintained language. And when it was being developed by Ihaka and Gentleman, it was explicitly made as an open source statistical analysis tool to address what they saw as a shortcoming in this kind of this aspect of the research world. So there are, to any sort of open source project, there are pros and cons to the ethos of the R language, and I think it might be best to start off with a couple of the cons. So because it's 20 years old and it's derived from this S language, there's a little bit of technical debt and some code oddities sometimes. And it also implements C and Fortran in some instances. You don't really need to know or care about what those languages are, just know that they're also even older than R and not always the most efficient or easy to work with. One of the other things that I find frustrating about R is that the error messages you receive are not always the best. You can't always interpret, if you write something incorrectly in your code. the messages that come up aren't always that great. They're just not really easy to interpret at the end of the day. And that's just kind of a personal complaint for me. Another personal but common complaint is that base graphics are just not something pretty to look at. Graphic design has come a long way in the last 2 decades. And so the graphic system that R originally shipped with is really out of date at this point. And there are a lot of solutions to that, but it is a kind of a core complaint about R. Something that's a blessing and a curse to open source software is that there's just a massive maze of packages. There are just so many options that it can be overwhelming and pretty easy to get lost into what packages you should use or select when you want to do data cleaning, data modeling, or any sort of visualization. And when it comes to kind of covering those topics, though, I would recommend that you go back and watch the Tidyverse presentation from last week, because I cover kind of some of the essential packages within those fields. But the biggest problem that I've encountered with R, and in fact, I was just discussing with Jen prior to the beginning of this recording, is that there can be a really steep learning curve to R. It's not always the most forgiving language. Like I said, it'll give you error messages, but it won't really tell you what to do. And really the best way around this is just to try and learn and keep going to presentations, or, you know, kind of go to the best resources that you can find and try and learn from those. So if any of those are, you know, some sort of a deal breaker for you, there are alternatives to using R. Some of the most common ones would be, you know, within our field, within research in particular, would be SPSS, SAS, and MATLAB. SPSS is actually the most popular language over the last 2 decades when it comes to academia. It's followed closely by R, which takes 2nd place. And then SAS is in a far 3rd, followed by MATLAB. And then everything else kind of is a, you know, small fraction of what people use in academia. Python and Julia are kind of the 2 other emerging or somewhat present options already. I think people like Python because it's a good general purpose coding language, and it has some good data science libraries as well. It's not quite as developed as R is in the data science realm. And Julia is not that present right now, but it is kind of an upstart language that could be really big in 10 years. It has a really strong emphasis on execution speed. So if any of those interest you, or you find that there's something about R that just makes you never want to use it, these are probably the next 5 languages you want to take a peek at. So from there, let's go to some of the positives, which I really think outweigh the downsides of R. So one of the best things about R is that it is, it's free now, and it always will be. So anything you type now, anything you save, anything you do in R is always going to be free. You'll always be able to execute it at a later date, and you'll always be able to share it. And this is something that SAS, Stata, SPSS, MATLAB, they can't say this. They all cost money. You're not necessarily going to be able to take your work somewhere else. One of the other great things about R is that it's exceptionally well documented, and there are great help networks available at Stack Overflow, the RStudio community, GitHub. Basically, anytime I've ever had a question about how to do something in R, I've been able to find an answer just by Googling it. One of the other great things about R is that it's quickly becoming a standard in both research and data science jobs. And in fact, it's being more and more widely taught in universities. I think that it's pretty safe to say that your current and your future colleagues will know at least a little bit of R, or even become domain experts in it. As a little bit of an anecdote to that, the Berkeley Data Science program, and I believe pretty much all their data science courses are now taught in R, and Berkeley is the largest pipeline of clinical research coordinators coming to the MAC. So that's definitely something to keep in mind about the skills of your future colleagues and research coordinators that you hire. And one of the other kind of incredible things to look at is just that there's been a massive growth in the number of open source packages available in R. So this plot that you see here is the number of packages that are published to CRAN, which is the main kind of package location from the years about 2000 up to, I think, 2018-ish. And you'll see that's really picked up in the last 5, 6, 7, 8 years or so. So people are really catching on and using it a lot more frequently. If you ever need to, there are, you know, functions or packages that let you do things like make QR codes or websites or do machine learning and other sort of like big data outsourcing packages. So pretty much there's a sampling of everything that you would ever want to do. What I think people are going to care about most here is doing analysis with R. And R really has some great packages for any sort of basic or fundamental analysis techniques that you might implement. So some of the stuff that pretty much everyone is going to be doing here is some descriptive and inferential statistics. So the stats package has tons and tons of built-in measures or functions for measures of central tendency, dispersion, skewness, or if you need to do some inferential approaches, there's tons of stuff that's pre-built for hypothesis testing, regression models, GLMs, and basically other population estimators. It's all built into the stats package, which comes shipped with R. Something else that I think is going to be, of use to so many people at the Mac is the psych package, which extends a lot of the, kind of common psych or neuropsych analyses that I know are performed at the Mac, like principal component analysis, item response theory, cluster analysis. Basically, someone's built functions to do all of these for you. So you don't have to worry about doing the math or how to do anything else. They're just there for you. And the last package that I've listed here is the summary tools package. I haven't validated this one myself, but it's got some pretty good feedback on just additional descriptive statistics. The overarching idea here just being that the tools you need already exist in R to do the analyses that you want. If you want to go even further, there's a huge variety of machine learning packages. The MLR and Caret packages will answer any sort of classification or unsupervised learning tasks that you may want to complete. I've used the MLR package. I really like it a lot. Caret is the other most highly reviewed one. I've not used that one, but people seem to like it. And something that I keep seeing come up pretty frequently is, I suppose, researchers at the Mac performing linear mixed effects models. And so the NLME package is another good one to look at if you have a desire or a need to kind of work with LMEs. And this is possibly not super applicable to people at the Mac, but if you are someone who's looking at doing really big data processing, something on the gigabytes and above orders of magnitude, there are packages that let you outsource to some big data processing or interface with things like Apache Spark, Hadoop, Storm, if you find yourself, like I said, dealing with just large amounts of data. So this is kind of like a very quick overview about why R is good for analysis, from anything from handling large data sets to basically doing the types of analyses that you actually care about. So from there, I think we'll just do a quick start on R. I'm just going to quickly overview what you should download and how to open and use some of those tools within R. So the first thing you'll need to do to get started with R is download it. You can find it at our project website, or if you open up the slide deck, you'll see that there's a hyperlink to download R there. Something that's technically optional, but I think is pretty useful, is to download Xcode if you're on a Mac, or download the R tools package if you're on a PC. These packages or these programs are needed for compiling some R packages. It's not something you really need to worry about the technical details for. Just do it and it'll probably make things easier for you in the long run. The last recommendation or thing that you should download is RStudio's interactive development environment. This is technically optional, but the IDE is really a massive improvement over the base R tool for writing code. The only time I've ever brought up the original R program for writing my code is when I do it accidentally. So I think that might be telling that RStudio is probably the way to go. It really is a convenient way to interactively write, run, edit your code, and view it all kind of in like the same pane. So I'll quickly show you what that looks like. So here we have basically an overarching view or the appearance of RStudio. And you can ignore any sort of specific text that I have up here right now. What I want to highlight is that you can kind of divide it into 4 major sections that are referred to as the source, the environment, the console, and the viewer or help window. So the first one that I've highlighted here is kind of the source window. It'll contain all of your open R and RMD files, and you can run scripts by pressing the source button, or run the code that you've written up here line by line by pressing the run button. This is probably where you'll spend most of your time, kind of interactively creating code. The next portion is over here, highlighted in purple. It's called the environment window. And it'll show you all the objects that have been read into your environment, basically any sort of data sets or other variables that you've made. And in this case, you can see that I don't have any objects over there, but they would appear kind of in that blank space where it says environment is empty if I had some. You'll see that there are two other tabs here called History and Connections. History will quickly show you the history of all the lines you've run in that R session. So if you happen to run something, delete it, and say, oh my God, I want that back, you can go look in history. And then connections is if you connect to a database or say like a SQL connection to analyze some of your data or pull data. Next section is the console. The console is going to show you the code you just ran, and we'll print out the results of that code. You'll see that there are also tabs for terminal and jobs. A terminal is where you can run sort of bash or shell commands, and jobs will tell you if there's anything actively running in RStudio. So if you want to kill a process that might be slowing down your computer, you can go over there. And the final view to look at is the viewer or the helper. And there are a bunch of tabs here. The one that I usually keep open is packages. And it'll show you all the packages you've downloaded and options to install or update existing packages, or you can press the little boxes to make a check mark, like you see right here next to base, and that will load the package into your session. The other ones that you see up here are files, which will show the files available in your current working directory. Plots will show you any sort of plots that you've generated during your session. Help is where help windows will pop up if you use the help function. And the viewer will open kind of various other R objects that aren't necessarily plots or help files. And I'm not going to cover it in any detail, but it is something that exists. So I know I had mentioned R scripts and R markdown files in the previous slide. So what are those? At the core, both of them are files where you can write executable code. And R scripts are pretty much just for writing executable code. You can sprinkle in some notes as well if you want to document your code, and they end with a .r extension. But that's pretty much all I ever use an R script for. R markdown files interweave the code that you've written with actual text into a kind of nicely formatted document. It's really useful for report writing. Sometimes people have done it to actually, create an entire paper that they would publish or send to an academic journal, and they'll do it all in a single R markdown file. And these end with .rmd extensions. So in order to use both of these, of course, you need to know how to pull them up. So I'm going to do just a 90-second tutorial on opening and using these documents. So you see in this clip, the first thing you want to do in RStudio is go up to File, New File, and then click on R script. And just like that, you have your R script open. You can type in some code. In this case, I'm reading in a package. And next, I'm going to write just a little bit of code. And all of this is just being written and run interactively in my R script. And again, you'll see that all of the results from what I've run are listed in the R console down there. The other file type is an R markdown. You go through the same process, File, New File, R markdown, and it goes through a couple of different steps. In this case, we're being asked to enter a title and then choose the output options. It's really cool. You can choose between HTML, a PDF, a Word document, all different types of output styles. In this case, I just left it as an HTML document. You'll see that my title is there. And if you scroll up and down, this is kind of what a default R markdown looks like, with code chunks and text interwoven throughout. And those code chunks are kind of the grayed out spaces that you'll see. And when you try and knit it, which is the button I clicked previously, it asks you to save the document, and it will knit a document. So what we have here is a nice HTML output of basically all of my code, results, and other writing or documentation interwoven together. And it's a really nice format, and it's definitely something that I use pretty frequently. So those are the two kind of major options that you have when actually trying to write or create reproducible scripts or documents. So now that I've done a little bit of a quick start, I want to jump to some of the most important topics that you'll need to know about when using R. So this is going to be the bulk of the presentation and really the more advanced portion of the presentation, but it will also provide some of the more tangible info that you need on how to write code in R. So I'm going to cover a ton of topics, and I really hope that you learn a handful of things, but like I said at the beginning of the presentation, you'll probably have a number of questions, and it's best to Google or ask me if you have additional questions. So to get started, the topics that I want to cover are syntax, infix operators, classes, functions, loops, and data tables in R. So these are some of the most essential things you should know about. And once we get through kind of these 6 topics, I'm also going to close out the presentation with some troubleshooting and help tips. So moving on to syntax. So I'm going to start with a little bit of simple syntax. In order to assign an object or create an object, you can use this less than dash, or you can use an equals sign. The first one is kind of the preferred notation in R, and basically object assignment just means that you're creating a variable, and this is how you do it. So if I want to say that my object is assigned the value of 1, then I would say something like my object, less than dash 1, and it's pretty much just that simple. The other thing, next thing to know about would be functions. So calling a function, when you actually want to use something or do some sort of analysis is pretty straightforward. You would write the name of the function, you would write a single parenthesis, and then basically list out the arguments that you want to specify within the function, and then close off that function with a parenthesis at the end. And we'll talk a little bit more about arguments and what goes into a function on later slides. Something else that I also had mentioned was kind of adding notes to your code, or annotations, things that people can go back and read your code or read notes about your code, but it's not actually executed as code. And in order to do that, you just use this little hashtag sign, or octothorpe if you want to be old school about it. But basically you can write a hashtag anywhere in an R script or an R markdown file, and then just write out some text, and everything that's there won't be executed, just read. A couple of important things to know is that R has what's referred to as reserved namespaces. So you can never assign an object any of the names that are listed in that first sub bullet point. And you should also know that you can never name an object that begins with an actual number or begins with the underscore. R won't be happy about it. And the final note about simple, just really basic R syntax is that it's case sensitive. So lowercase a and uppercase a are going to be read totally different, if it's, if they're standalone letters, or if they're anywhere within a word or an object that you've assigned. So that's something that definitely messes me up sometimes when I'm coding, is that I'll accidentally have something that's upper or lowercase that shouldn't be. So definitely be mindful of that. So with that really quick overview, what does basic syntax look like in action? So what I've done here is just done a couple of simple assignments. You'll see that starting at line 3, I've assigned an object, and I've called it my object, and I've given it the value of 4. The following line is a note. As you can see, it's me just saying this is a note. Everything after that hashtag on the same line is a note. And it's an IDE, RStudio IDE. It shows all this stuff kind of highlighted in green, so it's pretty easy to distinguish from all the code that you've written throughout the document. And then line 5 is just a simple call to a function. In this case, I've called the mean function, which takes the mean of the object that I'm sending to it. And in this case, I've assigned the value of 4 to the variable called my object. So if you take the mean of 4, obviously the value is just going to be 4. This is a really, really simple example that I just wanted to demonstrate. And if you look down at the console down here, you'll see that I've run this line, mean, my object, and the output is 4, as you would expect. The following lines, 7 and 8, are just examples of bad assignment. So I tried to assign the value of 10 to something that starts with an underscore. And again, if you look down at the console, R doesn't know what to do about that. And in the following line, I tried to assign a value to something that starts with a number. And again, R doesn't like that. It says there's an unexpected symbol. So those are just some really quick and simple examples of what to do and what not to do with R syntax. The next topic I want to go to are infix operators. And these are used for really some basic operations that you can do in R. So what exactly are infix operators? They really are for things like, they enable functions or methods that are really basic expressions, and they come from their placement between two operators. So, this might seem a little nebulous, but really just means is that you have, in most cases, things like arithmetic operators, addition, subtraction, multiplication, these symbols would fall in between two variables or two objects. There's a more complete list available at the linked website, but these are some of the most essential ones that you're going to see. You'll probably notice that up until the greater than, less than, or greater than or equal to, and less than or equal to, all of those are all arithmetic operators. The last three that you see on there, I do want to point out, somewhat especially. The third to last one, that's two equal signs, is to basically evaluate if two objects are equal to each other. And the last two, the ampersand stands for and. So if you want to do multiple evaluations or operations with and statements, that ampersand is how you do it. And if you have operations that require an or statement, that vertical bar stands for or. And so talking about a lot of those essential operators, namely the greater than, less than, brings us to this idea of a Boolean. And Booleans represent logical values. Basically, a Boolean is a false or a true, a no or a yes. And R represents Booleans numerically as zeros or ones. This is kind of done invisibly, but it's important to know because you can do calculations with Boolean values. So how do these go with infix operators exactly? Well, a lot of these operators, like I said, are for comparisons, like the greater than and less than, equal to, and so on. And so the result you would get from basically doing an evaluation like that would be true or false, which are, again, just Booleans. So it's worth understanding that R treats Booleans as zeros and ones under the hood. So if you ever want to make, say, a truth table and you want to know, basically how frequently something is equal to another value, this is something that you can do because you have these Boolean values that are showing whether things are false or true when you make a comparison. So if I write code that says 5 is equal to 4, the result is going to be false. And that's just a really simple example, but it is how it works. And that false is going to be stored as a 0. To the next topic, we're going to talk about classes. And classes are really the essential topic, I think, for today. They're going to help you the most when it comes to kind of troubleshooting your code or issues that you might have. So talking about some of the classes or the data types that exist in R, first we want to talk about what is a class. So a class is just underlying object information. They're bits of info that describe your object. And the class of an object determines what a function can or cannot do to the object. So for example, I can't use a function to find the average of a word. That just doesn't make sense. They're totally different data types, and that's really all that this class idea differentiates is, what type of data you have. So classes really matter when it comes to running your functions and troubleshooting issues you might be having with actually, running functions and getting a sensible value or getting any value at all. So what are the major data types you should be concerned about? There are 4 that we're going to discuss. There's logical, there's double, integer, and character. And the double and integer I've wrapped in parentheses because they can actually be more broadly grouped into a single parent class called numeric, which we're going to discuss a little bit later on. So starting with logicals, these are essentially just another name for Booleans. They just return true or false values, which you can shorten to TF rather than the full true false. And again, their logical values are stored as integers internally. So 0s for false and 1s for true. Like I said, logicals are effectively just Booleans. Going on to numeric, or doubles and integers. So like I mentioned, numeric is just a general name for either integers or doubles. It's kind of the parent name, and you'll see all 3 of these names tossed around, but at the end of the day, they're all just numbers of some sort. Um, the major difference between integer and double is really only apparent with any sort of processing speeds, and you can declare integers explicitly by typing an L at the end of the name, but you might see this sometimes in older tutorials and troubleshooting guides, but it's really fallen by the wayside due to advances in computing power in the last 5-10 years. So no one really cares about making things integers anymore for the most part. Like I said, all three of these things are just indicating that some sort of data that you have is a number. And the final class or data type that I had mentioned are characters. And characters are just strings of letters, words, or any other type of character or alphanumeric value. And if you say mix numbers in with letters, then they're going to be registered as characters. But most of the time, R does a pretty good job about registering numbers as numbers and characters as characters. It's just when you intermingle the two, most of the time R will kind of think that it has characters. So what can you do with strings? You can use different types of string manipulation methods on characters to, say, extract, edit, substitute, or search for certain combinations of letters and words. This is really useful if you're doing different types of maybe text processing, NLP, or even if you want to do stuff as simple as like renaming columns in your data tables. So unsurprisingly, you can't perform math operations directly on characters. I think this is a little bit of an obvious point, but I think it's also useful to point this out just as a troubleshooting tool. There are definitely many, many times when I've tried to run a mathematical function on some sort of data, and I come to realize that R has decided that that data is actually a character. So this is something that I'm going to teach you how to troubleshoot a little bit later on, but it's worth keeping this idea in mind. So I've told you about these different data types, and they all work together. So this is kind of what's called the atomic hierarchy. And you'll see the 4 major data types listed below. And what I really want to point out is that they all point to this idea of atomic. And more importantly, atomic then leads into what's called a vector. So I don't know if everyone is familiar with what a vector is in R, but in summary, a vector is basically a sequence of objects where all of the elements within that vector are of the same data type. So that last part I mentioned, that everything is of the same type or class, is what this idea atomic means. So I want to repeat that. An atomic vector is a vector where every element in the vector is the same class. So when I make a vector in R, it will force the vector to be atomic, and it can do that by forcing individual objects in the vector sequence to change their class. This is called coercion, and it explains the hierarchy you see below, where logicals are the most specific data type and characters are the least specific. So if I try to create a vector that contains true, false, which are both logical values, and I add the value of hello, which is a character, the lowest common denominator in that entire hierarchy is character, which is going to make my entire vector a character. And the other thing I just want to quickly point out here, like I've mentioned before, is that integer and double both fall under this numeric classification. Again, not a huge thing, but worth knowing. So I know what I explained may sound a little bit confusing on the surface, so I want to take a quick peek at how this works in action. So what I've done here is I've created a bunch of vectors, and every item in a sequence is separated by commas. You'll see that there's this, if you look at line 4, for example, there's this C parentheses, some value separated by commas, and then an ending parentheses. And all I've done there is just create a vector. And on line 4, I've created a vector of numbers. In fact, the first 3 examples that are highlighted here is it's a vector of numbers, a vector of logicals, and then a vector of characters. And you can see that the results when I run this class function on these different objects is that, unsurprisingly, the numbers come out as numeric, the true false logicals come out as logical, and the characters that I put into the last one on line 10 come out as character. So the latter 2 examples demonstrate the idea that I was getting at, where there's this hierarchy or forced coercion of classes. So starting at line 13, I've made an object called mixed. And it's a vector where the values are true, 5, and 3. And again, we know that true is illogical, but 5 and 3 are numeric. So when I run the class function to check what class my object is, you can see that the output is numeric. And the last one, the last example I have here called, labeled on line 16 is mixed 2. It's a little bit of a tricky one. I put the logical true. I put another true, but this time I put it in quotes and I put the number 1 and then I ran the class function. And in this case, maybe this comes as a surprise to you, but the output of this is character. And this is just a little thing that I want to point out is that when you put anything in quotes, R reads it as a character. So that's why in this example, the lowest common denominator is character, because we have the word or the character true rather than the logical true in the mixed 2 example on line 16. So just other things to keep keep an eye on when you're writing your code or trying to troubleshoot. These are things that can trip you up when a class may change. And I think hopefully this discussion of the atomic hierarchy helps you understand how things might get changed to an unexpected class. A related topic that doesn't exactly fall into this data, this data structure hierarchy are what are called factors. And they're really closely related. They look just like characters most of the time. So a good example of, factors that look like characters would be the results easy, medium, hard. Those are natively characters, but you can change them to factors. I think for a lot of people it would make sense to do that if you were to, for example, have easy, medium, hard as answers on a Likert scale. They are ordered or ordinal, and you can declare factors using the factor function, and you can set levels. So obviously when I say levels, you can think of, well, obviously the order for easy, medium, hard is just that. But R is going to use alphanumeric order if you run that factor function and you don't specify levels first. So R, if I wanted to turn the labels easy, medium, hard into a factor, it would think that the levels are actually easy, hard, medium, because it's going by alphanumeric order. So just keep in mind that if you want to declare a factor, you should explicitly declare what the levels are. And I suppose the final question to answer here is why you would want to use factors. Like I said, it's ordinal data. I think that it's something that you would want to use for group analyses. Maybe a function that you're doing requires it. I think a good example of this would be if you're plotting data or results by different disease cohorts. You'll need to make sure that your disease information is labeled as a factor, so that your plotting functions know that they need to split all the data or all of the, say, linear regressions based on disease cohort. So a little further discussion on factors is that factors also contain levels that are represented by digits. This isn't something that you'll see explicitly. You're not going to see, the easy, medium, hard represented by the numbers 1, 2, 3, unless you ask R to do that for you. But it is good to keep in mind that the underlying data structure is an integer when you're dealing with factors. And I know this is a lot of information on factors, so I think that it is something that's worth troubleshooting, taking a look at. Some of the important functions that exist in base R are the factor, ordered, and relevel functions. And there's also the forcats package from the tidyverse, which will help you kind of, divvy up factors how you need them to be. So the other thing that is important now that we've kind of gone over an overview of the different classes is how to check classes. You often need to check them or convert variables between different classes. And in order to check classes, you can just run this class function, which is what I did in my preceding examples. And you can also run these explicit, is.factor, is.numeric, and so on functions, which will tell you true or false if something is a factor, numeric, and so on. And if you need to change classes, there's a whole nother set of functions that basically have the same naming conventions where instead of is dot factor, you can say as dot factor or as dot numeric to change a vector over to whatever class type that you need to use. Next topic are functions, and I want to talk very briefly about them. So the general format for a function is that you supply an object and you supply a set of arguments. And the object that you're normally going to supply to a function will be a vector or a data frame. And I think the standard is to kind of make the, the first argument for every function is going to be that object, that vector or the data frame that you're supplying. And then everything that follows after that first comma is going to be just additional arguments. So when you're writing out your functions, or you're calling a function, you should always name your arguments explicitly. So what that means is that if you, if a function has a placeholder for maybe an argument called remove NAs, and it's a logical where you can change it true or false, then you should always write out remove NAs equals, true or false. You should always write that. R will accept positional matching of arguments and partial name matching. So if I were to write remove N equals true, it would still understand that I'm asking it to call the remove NAs argument. But like I said, you should always name them explicitly just to make sure that your code is clearly written and that you don't have bugs in it. And the ideas that I just covered kind of stand true for both user-defined and built-in functions that you might encounter. So just to do a quick example of what functions would look like in a script, I've again called the mean function. It's just a built-in function to find the mean, and the first argument, x, is a placeholder for values that you're evaluating. So you see that line 3 is just me writing mean x. X isn't assigned to anything, there's no value there. But in line 4, I've said that the mean is equal to this vector of values, 4 and 5. Unsurprisingly, the results of that would be 4.5. And line 5 is what I was talking about with positional matching. So in this case, the first argument that goes into mean is x. But I haven't named x, I've just put a value right in that place. And R will still run that code, and it will understand that x is equal to this vector, which is 4 and 5, and it will still run the function. And like I said, I don't necessarily recommend doing this, especially when you're getting started with R, but it is something that can be done. And I'm not going to go really into the details of this, but lines 7, 8, and 9 show an example of a user-defined function that's assigned to the variable my_mean. So if you use what's this function call, literally the function on line 7, this is basically how you start defining that you want to create your own function. And you put in the arguments that your function is going to accept into the parentheses here. So you should see my mouse hovering over the x. And this is the only argument that my function has. It's the only value that I would need to supply to my function, my mean, if I were to, run it later on. And you'll see that inside of this, there's the body of the function, which has this return, sum, length, bunch of parentheses. And basically all that's happening is that if I run this later on, run this my mean function later on, the value, whatever value I put equal to x is going to be passed to this function sum and this function length, and whatever the result is going to be returned to me. This is really, really quick overview of kind of declaring a function and what goes into the function body. There's tons more to cover, but just wanted to give people a quick idea of how you could write your own functions as well. So the next major topic that I want to talk about, or not talk about, is for loops. So you can use for loops for iterative processes and code execution in R. Most languages, pretty much every language, has a way to write for loops. But R is already a vectorized language. So any sort of object you create is stored as a vector, and functions know to look at each I, or the ith object in your sequence automatically. Why does this matter? It's because for loops are really, really slow in R. They are kind of disregarded because R was written as a vectorized language, and so the need to kind of iteratively create or execute things just wasn't prioritized in any way. I also think that for loops are pretty difficult to read, so the comprehension of them can be difficult at times. I've never needed to write a for loop statement in R, and like I said, you should probably do your best to avoid them. If you look to the tidyverse or maybe other statistics packages, you'll be able to find pretty much any solution that you'll need that for any approach, any sort of question or difficulty you might be having with your data can be addressed by someone's pre-existing functions. So that's one of my biggest recommendations, is just never consider writing a for loop in R. Final topic that I want to cover are data frames. So what is a data frame? It's just a tabular data representation. Pretty much all of you are going to be familiar with CSV or Excel files. You can consider all of those different types of data frames. And this is just a generic term for a 2D format where each row is an observation and each column is a different variable. And there are 3 different implementations of data frames within R. There is just the base implementation where they're referred to as data frames. There's the data table package where, unsurprisingly, this 2D representation is referred to as a data table. And then finally, there's the Tibble package, which is part of the tidyverse packages I covered last week. And like the data table package, the Tibble package names its tabular data as Tibbles. At the end of the day, all 3 of these are pretty much exactly the same. They're just 2D representations of data. Pretty much every function that works with one type of representation will work with the other. But I think Tibbles are the best one, and you'll see how now. So the base R data frame is slow, and its printing method is kind of ugly, just like the graphics that I mentioned earlier. Data tables are designed to be fast, but the printing method is still ugly. And Tibbles really are the best of everything here. Tibbles are simultaneously a data frame, a data table, and a Tibble all at once. They've done some fancy stuff under the hood to make it function as all 3 of these. So what it means is that it's faster. It's designed to work with everything in the tidyverse, and has this superior print method. And I know I keep talking about print methods, and you may be wondering, what is that? Why does this matter? So this is what it looks like when you print out a Tibble. And as you can see, Tibble shows us a bunch of different column names, the class of each column name, and we'll highlight in red missing or negative observations when you kind of look at this printout. And moreover, the Tibble prints make a lot of additional information readily available about the data set, including, say, any sort of additional variable names, which you can see listed out partially down here. And you can see the number of remaining rows. So you'll see in this case, we're given this kind of meta information about a data set called flights. We can see that it has over 330,000 rows and 19 columns, and that's printed for you really neat down at the console. And you don't really need to worry about ever explicitly changing your data or your data tables into a Tibble. If you use the read-in functions from the read-R and read-XL packages from the tidyverse, your data will automatically be a Tibble. And really the major advantage is that you get this really neat and easy to look at printout, so you can pretty quickly understand or visualize some of your data as it exists in its 2D format. So that was a quick overview of what I think are some of the most important topics. I know I kind of flew through a lot of different things there. And like I said, I do want to be available for questions at the end of this presentation. And I hope that some of what I taught you on those spurs you to maybe Google things a little bit more or look for additional training at some of those topics. What I do want to give now are just some additional tips and tricks that you can use within R that I think, or I certainly hope, will help improve your learning curves with R and just how you process data. So a couple of things that I recommend is sometimes just look at your data in Excel. I do this, I'm definitely guilty of, opening my Excel file, looking quickly to see what columns I have, roughly how big it is. The equivalent way to do that in R is to use this view function, and it will pop up your data frame or your data table, whatever you want to refer to it as, directly within R. It is a little bit slow sometimes if you're working with a really big data set, but if you have something that's pretty small, using this view function is also pretty easy without having to wait for Microsoft Excel to open. If you want quick quantitative information about your data sets, you can use the stir or str function on your data frame. And it'll basically quickly show you meta information. It'll tell you basically all the variables that exist within your data frame and what type of variable it is, and a little bit more meta information. The summary function is really useful, especially if you have numeric data. I think it gives you mean, median, like the 25th and 75th percentile values, and it'll do it for your entire data frame for each variable within your data frame. If your data is not numeric, it will also tell you, for example, if you have characters, it'll give you a little bit of information about the number of characters or different unique ones that are available. So those are two really good and quick exploration tools that I definitely use every time I'm looking at a fresh data set. If you're having trouble with your functions, there are two ways to basically get help. You can write question mark and then the name of the function. Don't add the parentheses at it, just say, a good example would be question mark mean. And that'll pull up the help page for the function mean. You can do the same thing if you just write help and then add the name of the function in there. They're exactly the same, just different shorthands, but they'll pull up these help pages. And this is an example of what it looks like. So we're now looking at the bottom right-hand corner of RStudio that I'd shown you earlier. And we're no longer looking at the packages section, we're looking at the help section. And we're looking at help for the mean function. And as you can see, this help page will tell you the name of the function, a brief description about it, and it'll tell you the order that arguments are supposed to be named. And then it also gives you what each of those arguments mean, what sort of value it's expecting. This is super, super helpful anytime you're dealing with a new function. I pretty much always go to the help page to learn how to run my functions effectively. And if you need more help than that, you can run this function called vignette, and it'll pop up basically a list of vignettes or short kind of examples, help pages that are available for the different packages that you've downloaded. And as always, you can Google your problem. You can go to Stack Overflow or the RStudio community. I mentioned earlier that pretty much all questions I've had have been already answered through some combination of these resources. GitHub I put up here just as, a potential idea, because basically every package you're going to download is open source. It'll probably be hosted somewhere on GitHub. If you have a bona fide problem or error that you're encountering with a package, you can basically open an issue with the package author on GitHub. But if you're just trying to troubleshoot, they don't take kindly to asking how to use things, just notifications that something is not working properly. A couple of additional troubleshooting cheats, I suppose, I have for people. If you find that a function is not running, let's say you open a fresh RStudio session, and for whatever reason, a function that was working last time is not working this time, something you can do is explicitly declare the package that you're drawing a function from. So I put this example filter here. So the stats package has a function called filter, and dplyr from the tidyverse also has a filter function. Sometimes R doesn't know which one to look for or which one to use. So if I were to write dplyr : filter, R then knows to pull the filter function from the dplyr package. This is enough of an issue for me, at least with the filter function, that I pretty much always explicitly declare the package dplyr for my filter. Just a little tip or trick. Something that, if your R is moving really slowly, there might be too many objects in your environment, or you might just find it difficult to keep track of everything that's in your environment. So if you want to get rid of everything that's like already there, you just want a kind of fresh session, you can run this first function that I've put under the useful cleaning functions. It will list out and remove everything that's active in your environment. And then if you want to restart your RStudio, run that bottom function, and it'll just give you like a fresh session. So with that, a couple of my recommended resources, I put these up last time. I really think that the best place to start is Roger Pang's and John Leake's Johns Hopkins University session on Coursera. And I think the best book to start with would be the Beyond Spreadsheets with R. It's a really approachable book that helps you understand R kind of from the perspective of coming from Excel. So with that, I'm going to open it up if people have any sort of questions. The slides are going to be available on my GitHub, and this video recording will be available probably within the next several days. So go ahead and stop sharing. And if people don't have any questions, that's good too. I'll hang out.
Pat, one question.
Yeah.
With the atomic ordering, you said does it always default to the more specific or the less specific of the
less
type?
Specific. Yeah.
Less specific. Okay. So if you've got like a character variable in there, it makes a character. I saw that. But
Character.
It considers logic to be less specific or more specific than numeric.
It is more specific than numeric. So logicals are, it maintains the fact that it's a 0 and a 1. So it is an integer, but it's not just an integer. It's a specific type of integer where your only values are 0 and 1, and it knows that it's a true false. It's a Boolean. So yeah, it's like just a little bit, like one step further beyond. All right, I think doesn't look like we have any other questions. So Jen, are you all set to wrap up the recording?
Yep, we're good. Thanks, everybody.
Great.
Thanks, Pat. This is great.
Thanks, Pat. Bye. See you guys next week.
See you next week.